Welcome to the deep dive. Today, we're looking at something, well, you see them everywhere in modern buildings.
Uh-huh.
Those recessed downlights,
Huh?
they look great, right?
Yeah.
Really sleek, integrated.
Absolutely. Completely ubiquitous design feature now.
But here's the thing. Every single time you cut a hole for one, you're actually creating a pretty serious problem, a weakness.
A life-threatening weakness, potentially.
Yeah,
You're breaking the fire barrier,
exactly. A path for fire and smoke.
which is why we have to talk about fire-rated downlights. It's mandatory, not optional.
Right. So the mission today.
It's really understanding the rules, the tech that seals that hole back up, and, crucially, how getting the installation wrong can just undo everything.
And you mentioned something specific there, compartmentation.
Yes, compartmentation.
Ugh.
That's the core idea. Keeping fire contained in one area, usually between floors, these little lights play a huge role in maintaining that.
Okay. So we've cut this hole. We've broken this barrier that's meant to give people time to escape. What's the required fix? What's the engineering?
Well, the mandated solution is the fire-rated downlight itself. It's specifically designed to restore that fire integrity where you've made the penetration.
And how does it do that? What's the magic?
It's clever stuff. Inside the fitting, usually within the steel body, there's a special material called intumescent material.
Intumescent. Okay, hear that term a lot. What is it? Some kind of plastic?
It's often a carbon polymer matrix.
Yeah.
And its reaction to heat is the key.
So what happens when a fire starts nearby?
Well, when it gets hot enough, say around 120, 150 degrees Celsius, this material doesn't just melt. It softens, releases these trapped gases, and it starts to expand.
Expand? How much?
Dramatically. We're talking like up to 50 times its original volume in some cases.
Wow. Okay, so it's not just blocking the hole.
No, it actively swells up to fill the entire gap. It forms this dense, hard char, almost like a rock plug.
A plug, right. Sealing the void around the light fitting itself.
Exactly. And that barrier stops, or at least significantly delays, the fire and the hot toxic smoke from getting through to the space above.
And that delay, that's the fire rating, measured in time.
Precisely. You'll see ratings like 30, 60, 90, sometimes 120 minutes. That number tells you how long that barrier is designed to hold under test conditions. Those minutes are critical escape time.
Got it. Now, before we get into the regulation side, you flagged something earlier that causes a lot of confusion. The difference between fire-rated and F-marked.
Ah, yes. This is so important and so often misunderstood. They sound similar, but they mean totally different things.
Okay, break it down for us, F-mark.
F-mark just means the fitting itself won't get hot enough during normal operation to ignite flammable materials it might be mounted on. Think wooden joists, insulation sometimes.
So it's about the light not starting a fire under normal use.
Exactly. Operational safety. It tells you nothing, absolutely nothing, about whether it will stop a fire coming through the ceiling from elsewhere. It doesn't seal the breach.
Right, so F-mark is just safe to install here, not stops fire spreading.
Correct. For stopping fire spread, you need that specific independent fire rating certification. Totally different test, different purpose.
Crystal clear. Okay, let's move on to the rules. You mentioned mandatory. This comes from UK building regulations.
That's right. Approved Document B, the fire safety part. It's very clear.
And what does it say about holes in ceilings?
It essentially says any opening you make in a fire-resisting ceiling, and most ceilings between floors are fire-resisting, must be, quote, adequately protected. Fire stopped.
So the downlight has to basically match the fire rating of the ceiling it's going into.
Precisely. If the ceiling is designed for 60 minutes of fire resistance, the downlight penetration must also provide 60 minutes.
And how does that translate practically? Does every ceiling need the same rating?
No, it varies.
Yeah.
For a standard ground floor ceiling in a house with maybe just storage above, 30 minutes might be enough. But the moment you have living space above another story, a flat, a loft conversion, the requirement usually jumps. You're typically looking at 60 or even 90 minutes then.
And for bigger buildings? High rises.
Yeah, for taller residential buildings, say over 18 meters or sometimes 30 meters, it can go up to 120 minutes. Depends on the overall fire strategy for the building.
Okay. This leads us to something you highlighted as really complex. The rating isn't just the light fitting, is it? It's the whole system.
Yes. This is probably the most critical takeaway. The fire rating isn't owned by the downlight alone. It's a classification of the entire ceiling construction. The plasterboard, the joists, and the correctly installed fire-rated downlight working together.
Why is that distinction so vital?
Because a downlight is only tested and proven to work within a specific type of ceiling buildup. The intumescent material is designed to activate and seal the gap just as the surrounding structure starts to fail.
So if you put a downlight tested for, say, a really robust ceiling into a much thinner one.
It won't work as intended. The thinner ceiling might fail much faster than the downlight expects, meaning the fire bypasses the protection. The certification is essentially void if the ceiling doesn't match the test conditions.
Can you give an example? Like, what's a typical 30-minute ceiling versus a 60-minute one?
Sure. A basic 30-minute ceiling might just be a single layer of standard 12.5 mm plasterboard fixed to timber joists, perhaps at 600 mm centers.
And to get to 60 minutes?
You usually need more substance, more resistance. So that often means maybe a double layer of plasterboard, or perhaps using a specific type of thicker fire-rated board. You're increasing the time it takes for the fire to burn through or heat up the void.
Right, delaying the failure of the main barrier.
Exactly.
And this ties into another complication, the type of joists being used. You mentioned solid timber versus newer engineered joists.
Yes, a huge factor often overlooked. Traditional solid timber joists behave quite predictably in a fire. They char at a known rate.
But things like I-joists or metal web joists, posy joists.
They perform very differently. I-joists, for instance, often have a very thin web, maybe OSB or something similar. That thin web can burn through much, much faster than solid timber.
So the whole floor structure could collapse sooner.
Potentially, yes, much sooner. This means the fire test for the downlight must specifically include the type of engineered joist you're installing it under. A test certificate for solid timber joists is not valid for I-joists.
Wow. So the installer needs to know the exact joist type above them and check the downlight's paperwork matches.
Absolutely, they must verify it.
Yeah.
The test certificate is the proof. If they use a fitting tested only with solid timber in an I-joist ceiling.
The fire rating is meaningless.
Correct. Legally non-compliant and, more importantly, potentially unsafe. It creates a false sense of security.
That's a heavy responsibility for the installer.
It is. Due diligence is crucial.
Let's shift gears slightly, away from the structural fire rating to the practicalities of installation. There's this big conflict, isn't there? The insulation trap.
Yes. This is where different parts of the building regulations can seem to clash. It's a really common issue on site.
Explain the conflict.
Okay, so Part L of the regs, that's about conservation of fuel and power, wants you to insulate ceilings really well. Pack that loft space with insulation to stop heat escaping. Energy efficiency, right?
Makes sense, but
But most standard downlights, even fire-rated ones, generate heat, and they need airflow around them to dissipate that heat safely if you just bury them under a thick layer of insulation.
problems.
Two big ones. First, overheating dramatically shortens the life of the lamp, the LED, the driver. Things fail quickly.
Okay, annoying but not dangerous.
Well, the second risk is dangerous. Trapped heat can build up over time, even with LEDs, which are cooler than old halogens.
Halogens were terrible for this, weren't they? Like little heaters.
Exactly. They could easily get over 200 degrees Celsius, well into ignition temperatures for dust or timber or insulation itself.
Yeah.
But even trapped LED heat can potentially lead to smoldering or ignition over the long term. It's a fire hazard.
So Part L says insulate everywhere, but basic fire safety says don't cover the light. How do you solve that? What are the approved ways?
There are basically two main routes for compliant installation. The first is to use specific types of downlights.
The one's designed for it.
Yes, premium products, often labeled insulation coverable or similar. Brands mentioned in the sources, like Integral LED's EvoFire or Aurora's EFD Pro, have designs that manage heat properly even when fully covered. They've been tested for that specific scenario.
Right, so they cost more, presumably, but solve the problem directly. What's option 2?
Option 2 is more about managing the space around a standard fire-rated downlight. You install a physical barrier above the light fitting in the void.
Like a little hat.
Sort of. They're often called insulation support boxes, loft caps, or downlight covers. They create a mandatory air gap around the fitting.
Ah, so the insulation can go up to the box, but not directly onto the light.
Precisely. It maintains that crucial airspace for heat dissipation while still allowing the main loft area to be insulated.
Yeah.
It satisfies both Part L and the fire safety aspect.
Clever. Okay, so that's fire and thermal sorted. You also mentioned these fittings often tick other boxes too, other parts of the regs.
Yeah, often they do. Think about that hole again. It doesn't just let fire pass through, it also lets sound through.
Ah, acoustics, Part E.
Exactly. Part E, resistance to the passage of sound. Many fire-rated downlights are designed with good seals, often using gaskets, which also help block airborne sound traveling through the penetration, so they contribute to acoustic performance too.
Okay, fire, thermal, acoustics, anything else?
Moisture. If you're installing downlights in a bathroom, kitchen, or any potentially wet area, a zone 1 or 2 location,
You need water resistance. IP
it's
rating.
correct. Part C, resistance to moisture. So the fitting needs to be fire rated and have the appropriate IP rating, often IP65 for zones where splashes are likely.
So one fitting potentially meeting part B, fire, part L, energy insulation workaround, part E, sound, and part C, moisture.
It's quite remarkable, isn't it, how much engineering goes into what looks like a simple light fitting.
It really is. Okay, wrapping up with best practices and maybe alternatives. Installation seems key. We talked about matching the ceiling type, but what about the actual cutting?
Precision is vital. Obviously, all the electrical work needs to comply with BS 7671 Part P for domestic work. But physically, the hole size is critical.
Why? Too big is bad.
Very bad. You absolutely must not cut an oversized hole. The fire-rated downlight has a flange or bezel that needs to sit snugly against the plasterboard. If the hole is too big, that seal is compromised.
And the intumescent stuff might just squeeze out the gap.
Exactly. It won't be contained properly to form that effective char plug. It completely voids the fire rating. Use the specified hole saw size, nothing bigger.
Right. Get the cutout wrong, and the expensive fire-rated fitting is useless.
Pretty much, yes.
Okay. Now, what about, are there alternatives? Can you use a normal downlight and add something else? I think I've seen things called fire hoods.
Yes, fire hoods exist. They're basically flexible, fire-resistant enclosures or tents that you fit over a non-rated downlight in the ceiling void.
So are they a good substitute?
Well, the sources suggest caution. While they can be used and can meet regulations if properly certified and installed, they're generally seen as a fallback option, not the first choice.
Why is that?
They can be fiddly to install correctly, especially in cramped spaces. Ensuring a proper seal around cables and the ceiling itself can be tricky. And frankly, the testing and certification for an integrated fire-rated downlight unit is usually more robust and reliable.
So integrated fitting is preferred.
Generally, yes. It's a purpose-built, factory-tested system. Safer, also easier to guarantee compliance. If you do use a hood, make absolutely sure it has the right fire rating certification for the ceiling construction.
Good advice. Okay, final checklist then. For someone buying these or checking an installation, what are the absolute must-haves, the proof?
Right, 3 key things to look for. First, independent test evidence. Look for certification from a reputable body like BRE Global or similar.
Not just the manufacturer saying it's okay.
No, independent proof. Second, check for compliance markings. Standards like BS EN 6059822 and the UKCA Mark Now or CE marking.
Okay. And the third, most crucial one.
The actual fire rating, 30, 60, 90 minutes, and critically, evidence that this rating applies to the specific ceiling construction you have, the plasterboard type and thickness, number of layers, and, as we discussed, the joist type.
So you need the paperwork, and it has to match the reality above the ceiling.
If it doesn't match, it's not compliant. Simple as that.
This has been, well, illuminating. It really shows how a simple aesthetic choice, popping in some recessed lights, opens up this major fire safety challenge.
It does, and it requires a properly engineered solution, not just any old fitting. These fire-rated downlights are essential structural safety components.
Maintaining that compartmentation we talked about.
Exactly. And meeting all those building regs Part B is the big one here.
The level of detail is pretty amazing, isn't it? Fire, acoustics, moisture, energy efficiency, heat management, all in one small fitting.
It really illustrates the complexity of modern building standards, doesn't it? How even seemingly simple elements have to be carefully engineered and, crucially, correctly installed.
Which leads to a really interesting final thought for you listening. We talked about that tension, that conflict between Part L wanting maximum insulation and fire safety needing heat dissipation around the fitting.
That clash of requirements.
So thinking about that, how many other parts of a building, things that look simple on the surface, are actually these complex engineered systems balancing conflicting demands? Systems that rely entirely on someone on site getting the installation exactly right, interpreting test data correctly for that specific situation.
And what happens when those standards genuinely clash? Which one wins? It's a constant challenge in construction.
Something to ponder. A huge thank you for joining us for this deep dive.
My pleasure. It's vital information.
See you next time.